Now, as part of this course, you're expected to be able to prove this result, not just use it, but actually prove it. So you need to be able to work through this proof on your own in case you're asked to do so in an exam. Now, we're differentiating something that's got two parts multiplied together, and both of them are functions of x in their own right. So obviously, to do this, we're going to need the product rule. So if you like to write your ingredients on the side and then use them, go ahead and do it that way. If you can put it straight into the product rule, doing the working in your head, that's also fine. I've done it this way for anybody who needs it and can follow along. So I've reasoned that this is u. So when I differentiate that, I need to use the chain rule. I bring out the m. I differentiate what's in the brackets and get 1, bring that out as well, doesn't change it. And then I rewrite the bracket part and I drop my power down by 1. For the other part, v, it's some quotient, it's some polynomial in x. And I don't know what it is, I don't have the formula for it. So it's enough to say, look, I can just differentiate by calling it q dash x. So now when we put that in, we need to do v u dash, so we need this part multiplied by that part. You can write them in any order. Let's just go ahead and write them down exactly as they come. We have this part, then we have the m, then we have x minus alpha to the m minus 1, plus u multiplied by v dash. So we have the x minus alpha to the m part multiplied by q dash x. That's a little bit messy. I'll just keep them off to the side. Okay, can we tidy that up at all by factorising it? Well, the q of x and q dash x are different. This one has an m, this one doesn't, but both of them have got some of these. How many do they both have as a minimum? This many, isn't it? Because this is a number that's 1 smaller. So we can bring that out the front of some brackets and say they've both got at least m minus 1 of those. And then inside our square brackets, we're left with, well, let's write the m first, not that it really matters. M q of x plus q dash x multiplied by another one of these, isn't it? There we go. Now the part in the brackets looks a little bit complicated and messy. We can tidy it up to some extent by saying, look, we've got this important part out the front, which looks a lot like what we started with, but we've now got a power that's 1 smaller. And then we've multiplied it by some function of x in its own right. Now let's call this r of x because we've used p and q and it's the next letter. Now we could actually say there where r of x equals, and then we can write all this out, m q of x plus q dash x, x minus alpha. Okay, so we've defined what it is. Now let's think what's going to happen if we find p dash alpha. Let's just go back a step before we do that and consider how we use this fact here, how we use this. Now the factor theorem says that if we sub some value x equals alpha in here, then this part will turn to 0, and what we'll get is an answer of 0. And that tells us that alpha must be a 0 of the polynomial and x minus alpha must be a factor. And we can see that it must be because look at the format here. Now, if x minus alpha to the power of at least 1 is a factor of our polynomial, it makes sense factors always come in pairs. Something multiplied by something makes another number. So you always need to have a partner, if you like, for that factor. And the partner needs to not be 0 for the whole thing to make sense. Now let's come down to here and have a think about what will happen when we sub x equals alpha into this. Again, we're going to have 0 multiplied by something, but it's important to consider what that something will be. Because if it's also 0, then we've found a factor, but it doesn't have a partner. It sort of doesn't make sense. So let's consider what would happen if we found r of alpha. So subbing in here, where r of alpha would be, now r of x has two parts. It's got this part, and it's got this part over here. Sorry, that's a little bit messy. It actually says x minus alpha. It's a bit hard to read. Now, if I sub alpha into this part over here, I'm going to get 0, aren't I? So 0 times q dash x, whatever q dash x is, I'm going to have 0 for this part. So I'm just going to be left with m times q of alpha. Now, what is m? M is just a number that was the multiplicity of our original 0, wasn't it? So it's a number like 1, 2, 3, 4. It's an integer, right? And what is q of alpha? Well, didn't we just say, if you look back in your notes, that Q of alpha can never equal 0? Because if it did, then x minus alpha would be a factor of Q of alpha. And it's not a factor. We've put all of the x minus alphas, no matter what the multiplicity is, out the front there. So we know that Q of x can't be divided by x minus alpha any more times. That's already been done, and these are the leftovers. So that means if it can't be divided by it, and x minus alpha isn't a factor of it, then Q of alpha won't equal 0. Now, how does that help us? Well, it tells us that R of x, when we're subbing alpha in for it, is going to be a legitimate polynomial in its own right. It's not going to be 0. And we can tell that because Q of alpha won't be 0, and we know that m is a positive integer. So now we can compare this result to this earlier result and draw some important inferences from it. Oh, that should actually be R of alpha, not R of x, because here we're subbing in alpha, and I accidentally wrote an x, so maybe just change that in your notes. So our big important finding then is that x minus alpha to the power of m minus 1, right here, is a factor of p dash x, because look, you can multiply it by something else which is a legitimate polynomial in its own right, and they multiply together to make p dash x. And what that tells us is that if this is a factor, then x equals alpha must be a 0 of multiplicity m minus 1 of p dash x.